This is the fourth section of the integration chapter, and this is what they call the reverse chain rule. I actually call it looking for patterns. I call the reverse chain rule that when you integrate the outside, divide by the inside, differentiate. That's what I call the chain rule. So I call this looking for patterns. And what we're doing is we're looking for particular patterns in an integral so that we can try a certain answer. So for example, when you want to integrate something, so you're integrating something here, you might not know exactly what the answer is, but you might want to try something. So let's say you try some expression and you want to see how good your try is. Okay, now what you would do is you would get what you've tried and you would differentiate it. Now you may find that what you've tried, what you've guessed the answer may be, is completely wrong, or it may be that it's half as big as it should be, it's 3 times bigger than it should be. There may be some sort of multiple that we need to multiply it by to get it to work. So we've got an integration. It's almost like we do an informed guess at what the answer is, because it may not be something that's particularly obvious. It doesn't fit any of the other patterns. We differentiate our informed guess. We compare it to what the question was, and then we might need to make an adjustment. So when we get to this stage, okay, so we may need to make an adjustment let's spell it right, adjustment to our informed guess. Yeah, and that's what it's all about. So here you can see what we're looking for. So we're looking for, in this one, something that has that pattern. So basically you've got the top differentiated over the bottom. It looks a bit like that. Now there may be some sort of multiple that means, well, the top isn't exactly the bottom differentiated. Maybe the number's not quite right. Well, if that's the case, then we try log of the bottom. Let me give you an example. So let's say I had something like, I wanted to integrate I don't know, 3x over 4x squared minus 2. Now I can see that if I were to differentiate that, I'd actually get 8x at the top. Well, you know, it's apart from the 3, 8x, 3x, you know, that number that I need to turn the 8x into 3x is like the k. In terms of the powers of x, it's right. Yeah, the number's not correct, but it works out right. So what I will do on something like this, I will try the log of the bottom. So I will try the log of 4x squared minus 2. Now how do I see how good my try is? I differentiate this, and this differentiated, well, what does it happen to be? F dash of x over f of x. So if I differentiate that, I will have 8x over 4x squared minus 2. So I need to make some adjustment to my guess. I want the number 3 at the top, not 8. So if I take what I guessed and I divide it by 8, that gets rid of the 8. And then if I times it by 3, that now makes it right. So if I were to do 3/8 times that, yeah, it now works out right. So this would be the answer. So that's pattern number 1. F dash of x over f of x, basically. The second pattern is this. So you've got a function to a power, that's this part here, multiplied by that function differentiated again with some value of k. So a function to a power, and then you've basically got the function differentiated times by this bit. Now if you see something like that, what you want to do is you want to try the function f of x to one higher power. Probably best if I give you an example. So let's say, for example, I wanted to integrate something like 4 sine x cos cubed x dx. So it fits that pattern, what I've got in this part. So f of x would be cos x, I've got cos x cubed, and then this bit here, well, that's cos differentiated. I know the sign is not right and there's no 4, but we can deal with that. That's like the k part. So if we get something like that, what we're going to do is we're going to try the function that's to the power, which is cos. So we're going to try cos 4. So we're going to try that, and the way that we see how good our try is that we differentiate it. Now when I differentiate this, I can use the chain rule, because it doesn't matter about the bracket being linear or not. So I differentiate the outside, the inside of the bracket doesn't change, and you multiply by the inside differentiated. So that gives me something very close to what I started with. So I actually end up with this, but my adjustment, I need to adjust my guess. So if I stick a minus sign there, this now becomes my final answer. That's the correct final answer there. Yeah, so that's how this, what they call reverse chain rule, works. We're looking for patterns. So it's all about deciding which pattern does it fit. So A, I think that fits the f dash of x over f of x pattern. Yeah, because I'll get the right thing at the top. So I'm going to try, and you should always write down what you're trying. I'm going to try log of the bottom. Don't forget the modulus. So log of x squared plus 1. How do I check how good my try is? Well, I differentiate that, and if I differentiate that, I'm going to get x squared plus 1 at the bottom, 2x at the top. So I don't need to make any adjustment. Final answer is that it's just log of x squared plus 1 plus c. And I suppose the examples I did at the beginning should have also had plus c at the end. Never mind. Part B. Now let's have a look at this one. This one also fits the f dash of x over f of x pattern, because if I differentiate the bottom, I would get 2 cos x at the top. Now the 2's not a problem. Anytime you get any constants, don't worry about it. We can account for that. We can make that adjustment. But I would get sine at the top. So it's going to fit this pattern again. So what do? I try log of the bottom. So I'm going to try log of the bottom, which is 3 plus 2 sine x. Like that. How do I check? Well, I differentiate it. So I'm going to check. And if I differentiate that, at the bottom, I'm going to get 3 plus 2 sine x. And at the top, I'm going to get 2 cos x. Now, the question just says cos x, not 2 cos x. So if I stick a half here, that accounts for the 2. That cancels the 2 out. So I can say that my final answer is going to be half log modulus 3 plus 2 sine x plus c. And you'll see later on actually that plus c you can actually write in terms of log. That'll be more useful later on, but c, well, I might as well tell you now. we might decide that we're going to write c as log of something. Let's call it log of another number. Yeah, because it's just writing a constant in a different way. They're both constants. C is a constant, log a is a constant. The advantage with writing c as log a or log of something is then it can be put together with this. So then you'd have the log of this plus log a, and then you can use the rules of logs to put those two things into one expression, which may be useful. Right, I think a fits the pattern of f dash of x times by f of x to a power. So the f of x part is like the sine x, because it's like squared. The f dash of x is like the cos x. Again, we won't worry about the constant. We can sort that out later on by making our adjustment. So I'm going to try sine cubed x. So that's what I'm going to try, which we can write like this, sine cubed x. Okay, and how are we going to check that our answer is any good? Well, we're going to differentiate it. We can use the chain rule, because it doesn't matter about the inside being linear. That's only with the reverse chain rule. So 3 bracket 2 sine x there, and then multiplied by sine differentiate, which is cos x. Now that is exactly what I started with. Yeah, 3 sine squared x, 3 sine squared x cos x. So I don't need to make any adjustment. So I can write my final answer as 3 sine. Oh no, that's the answer, isn't it? I want the actual thing. So yeah, it's just going to be sine cubed x plus c. So that is A. Now let's do B. Again, it fits that pattern of f dash of x times by f of x to a power, because if you differentiate the this part here, the f of x, which is x squared plus 5, you get 2x. Doesn't matter about the 2. Yeah, so here this is what it's going to be. So the f of x is x squared plus 5, and that happens to be cubed. So we try x squared, oops, I was going to put x to the power 5, x squared plus 5, we try it to one higher power, we try it to the power 4. How do we check? We do the chain rule. So actually, I suppose it is the chain rule in reverse, isn't it, really? Because you're checking by doing the chain rule. So it must be the reverse chain rule, I guess. Right, so 4 bracket 3, the bracket doesn't change, x squared plus 5. And then you're going to multiply by the bracket differentiated, which is 2x. So that will become 8x x squared plus 5 cubed. Let's compare that to the answer. Well, I've got an 8 here, and I don't want that 8. So the thing that I tried, I'm going to stick 1/8 in front. So I'll stick a 1/8 there, like that. That will get rid of the 8, and you'll get the x and then the x squared plus 5 all cubed. So final answer is going to be 1/8 x squared plus 5 to the power 4 plus c. Let's just highlight that in case you are pausing it. Now this question here, it would be very tempting to look at this and say, well, it's a fraction, so it must be f dash of x over f of x. You know, cot differentiated is cosec, so yeah, it must be that, but there's a power 3. And if you expanded these brackets here, or did that to the power 3, that differentiated is not going to give you that. Yeah, so it must be the second pattern. So the first thing that we need to do is to write this and bring the power 3 bracket to the top. So we've got cosec squared x times by 2 plus cot x to the power negative 3. Now we've got that, it actually is the second pattern. And it's because of that power 3 that makes the difference. So you've got f of x and then, or f dash of x to the n. So in this case, f of x is going to be the 2 plus cot x, n is going to be negative 3, and the f dash of x is going to be cosec squared x. And we can check cot differentiated is cosec squared, and I know that because I've just used the table backwards. So going from here to here, from the right hand side to left hand side, you can use it to do differentiation. Yeah, if you use the table backwards, it's a differentiation table. Okay, so what do we try? We try what's in the brackets to one higher power, so it's 2 plus cot x. Now, because the power is negative 3, one higher power is going to be negative 2, not negative 4. Yeah, you always add 1 to the power. See over here, we try n plus 1. So that's what we're going to try. So I should write that down, that we're going to try that. We need to check how good our try is, and the way that we check it is we do the chain rule. So you let's do it down here where we got a bit more space. You differentiate the outside, so you've got negative 2, negative 3. The inside doesn't change. Then you need to multiply by the inside differentiated. Now cot differentiated is going to be negative cosec squared. Cot differentiated is going to be negative cosec squared. So we need to times by negative cosec squared x. So let's tidy that up. We've got a negative and a negative, so it becomes 2 cosec squared x over, I'm going to put the negative 3 back down at the bottom so I can compare it with the question. So it becomes that, that's what it equals. Notice there's a 2 here that I don't want, this 2 here. So what do? I take what I've tried and I stick half in front, and that will deal with the 2. So final answer is going to be half 2 plus cot x to the power negative 2 plus c. I hope I've been writing all the plus c's down. Right, next one. Now, so here we've got limits, and this one fits the second pattern because of this matches up to the f of x to the power n, and is this bit is sec differentiated tan. Let's have a look. Sec differentiated. Sec differentiated becomes sec tan. Now we need to be careful with this. I'll show you what we're going to do on this to get this to work. Now the first thing I'm going to do, so from 0 to theta, I'm going to write it as 5 sec x tan x times by sec 3x. So all I've done is write it in a different way. I've taken one of the sec x's from the power 4 and I've written it here because sec differentiated is sec tan. So let's put this in. This bit is your f of x. I suppose the 5 is like the k. So let's make that clear. Whoops. So sec. So basically this bit here is like your f dash of x. 5 is like your k. And then the sec cubed, that's your f of x to the power n, where n is 3 in this case. So can you see we didn't just go ahead and use the second one? That's something you need to watch out for. and that's probably only going to happen where you've got second tan and where you've got cosec. So don't just dive in. We may need to do this because sec differentiated is not just tan, it's sec tan, and we need to split it up, otherwise we're not going to get the right answer. So on this we're going to try what's the f of x to high power, so we're going to try sec to the power 4 x. Now notice if I didn't do what I did at the start, I'd be trying sec to the power 5 and it wouldn't work, and I'd be wondering what's going wrong. So let's check. Whoops, it's spelled check right, CH. Let's check. So the way we're going to check is we're going to differentiate it. Remember, this is the same as sec x all to the power 4, so you get 4, 3. The contents of the bracket doesn't change, so that's sec x. And then we times by sec differentiated, which is sec x tan x. And I've just got that from, again, using the table backwards. Do I need to tidy that up? Yeah, I suppose I do, because I've got sec cubed times by sec, so that becomes 4, let's change it around, tan x, sec to the power 4x. Now, can you see that I've got 4 here, but the original question has 5, so this is how we deal with it. Now, what number do I want to get rid of? I want to get rid of 4, so that goes at the bottom of the fraction. What number do I want? I want 5, so 5 goes at the top of the fraction. So the number that you don't want, you put at the bottom. The number that you do want, you put at the top. Yeah, so our thing differentiated up here, also integrated, is going to be 5 over 4 sec to the power 4 x, and we've got limits from 0 to theta, and we've been told that equals 15 over 4. So now it's just a matter of working out what that is. We're going to do it down here. So we will substitute in theta and then 0, and then we'll be well on our way to solving this. So 5 over 4 times by sec to the power 4 theta, when you substitute in theta, minus 5 over 4 sec to the power 4 0, and that equals 15 over 4. Now I need to make sure my 0 doesn't look like theta. That's a 0 there. Now sec is the reciprocal to cos, so to help us work out this bit, we'd work out what cos 0 and do that to the power 4. Now cos 0 is 1, reciprocal of 1 is 1, so all of this bit makes 1, so that means that the second bit just becomes 5 over 4. So we'll have 5 over 4 sec to the power 4 theta, and that equals that negative, so this bit here is going to become negative 5 over 4. I'm going to add it to the other side, and that's going to be 15 over 4 plus 5 over 4, which is 20 over 4, which is 5. I'm then going to times both sides by 4, and then divide both sides by 5, and that leaves me then with sec to the power 4 theta equals 4. We then find the fourth root of both sides, so then we get sec theta equals, now when you do even roots you always end up with a positive and negative root, and the fourth root of 4 is the square root of 2, so plus or minus the square root of 2. Then we'll do the reciprocal to both sides so we can do it on a calculator. So cos theta equals 1 or plus or minus 1 over root 2. We're going to do the cos inverse of both of those. Now we need to remember that we're only looking for a value of theta between 0 and pi over 2, and it just says the exact value, so there's only going to be one answer. So if we get anything that's not in that range, we'll just forget about it. We're not going to don't need to use a class diagram. We're probably going to get it as we work it out on a calculator. So I'm going to do the cos inverse of 1 over root 2 and see what comes up. That comes up as pi over 4. Perfect. That's the solution I want. There's no point trying negative 1 over root 2 or using a class diagram. I've got it straight away, pi over 4. So let's write that down. Theta equals pi over 4. Right, you should now be able to do exercise 11D on pages 302 to 303 in a textbook, and as usual, let's get rid of these because you need to memorize them. There we go. And try and memorize some of the others as well. Be good fun.